Platinum, a metal whose annual production is only about 1/20th that of gold, is so essential that without it, cars would struggle to meet emission standards. Hydrogen fuel cell technology would lose a core material, and even some critical medical devices would have difficulty operating reliably. So how have humans managed to extract and refine such an extremely rare metal at a time when the world is reducing its dependence on oil and gas and shifting toward cleaner energy systems? From some of the deepest, hottest, darkest, and most expensive mines on Earth, tens of tons of ore are crushed, separated, and processed just to yield a few grams of platinum. After leaving the mine, the metal continues through a refining process that takes months to reach the level of purity required for high-precision industries. Today, join Agriculture Insight as we explore the journey of platinum, from a metal once considered a troublesome impurity in silver to a strategic material leading the global clean energy transition. Each year, the entire world produces only about 180 to 200 metric tons of platinum, less than 1% of global gold output. It's so scarce that it raises an obvious question: why is such a rare metal still mined at all costs, instead of being replaced by more common materials? Platinum is often mistaken for silver because of its similar silvery white appearance, but in reality, it is nearly twice as dense, harder, and highly resistant to oxidation. Its origin is also unique. Most platinum was formed from meteorite impacts billions of years ago and is not evenly distributed across the Earth. Around 80% of global reserves are concentrated in the Bushveld complex in South Africa, one of the largest platinum deposits in the world, stretching over 230 miles with ore layers buried deep underground. The rest appears only in scattered, extreme regions such as Norilsk in Russia and the Great Dyke in Zimbabwe. Yet despite such limited and concentrated supply, platinum continues to be mined every year for one fundamental reason: it is nearly irreplaceable as a catalyst. From automotive catalytic converters and fertilizer production to hydrogen fuel cell technology, platinum enables chemical reactions to occur faster, more stable, and more efficiently, under conditions where metals like nickel or copper cannot achieve the same performance. What's equally remarkable is that platinum doesn't simply disappear after use. Thanks to its chemical inertness, it resists corrosion and degradation over time, making it highly recoverable and recyclable. As a result, when a vehicle reaches the end of its life, its catalytic converter still contains platinum that can be recovered almost intact and fed back into the supply chain with its original quality preserved. This means that despite its extreme rarity, platinum is not only mined from deep within the Earth, but also remined from the very products we use every day. And now let's descend deep into the platinum mines around the Bushveld complex, the complex that holds the largest reserves of platinum group metals in the world. Unlike gold or diamonds, which can form in concentrated deposits, platinum is dispersed in extremely thin ore seams, sometimes just 8 to 12 inches thick, trapped between layers of magma that solidified more than 2 billion years ago. To access these narrow seams, the mining process begins by breaking the rock. About 2 miles underground, where rock temperatures can reach up to 140 degrees Fahrenheit, workers operate in low, hot tunnels where movement is restricted and ventilation must be tightly controlled. Here, the rock is broken using 2 different methods, with drilling and blasting remaining the most common. Industrial drills are used to bore deep holes precisely along the ore seam, after which explosives are placed into each hole and detonated to fracture the rock. At the same time, in some areas, large disc cutters are used as an alternative. These machines can weigh tens, even close to 200 short tons and rotate continuously, generating immense mechanical force to cut and crush solid rock layer by layer. Once the rock is broken, it is collected by loaders, transferred onto conveyor systems, and moved to the mine shaft to be hoisted to the surface. This entire operation exists to recover an extremely small amount of metal. On average, about 10 tons of ore yield nearly 31.1 grams of platinum group metals, with platinum itself making up only a fraction of that total. Despite working under such harsh conditions, a platinum miner in South Africa typically earns just over $1,100 per month, while many contract workers earn significantly less, even as fatality rates remain high year after year. In 2023, a cage carrying workers plunged about 650 feet down a mine shaft, killing 13 people and injuring more than 70 others, marking one of the most serious accidents in the platinum industry in decades. But this entire mining process is only the beginning. Once it leaves the deep underground tunnels, thousands of tons of raw rock are transported directly to the processing plant, where value lies not in the volume, but in the tiny amount of metal that can be extracted from within. First, the ore is fed into hoppers and passed over steel screens for coarse sorting. While smaller fragments fall through, larger rocks are retained and broken down using high-powered hydraulic hammers, which strike the surface directly until the pieces are small enough to pass through the screen. At this stage, the platinum is still locked within the rock structure, so the ore is transferred into massive rotating mills, steel drums stretching tens of meters in length, turning slowly but continuously. The core principle of this system is that heavy steel balls inside the mill collide constantly with the rock, generating thousands of impacts that gradually break the material down with each rotation, from solid rock into gravel, and then further into fine particles almost as small as sand. The entire process is automatically controlled in real time, ensuring the ore reaches optimal fineness before moving on to the separation stage. After being ground into fine particles, the ore moves into the separation stage, where platinum group metal particles are finally separated from the worthless rock using flotation. The mixture is fed into large agitated tanks and treated with specialized chemicals that make the metal-bearing particles hydrophobic. When air is injected, millions of tiny bubbles form. The metal-containing particles attach to these bubbles and rise to the surface, while the waste rock remains hydrophilic and sinks to the bottom. This process does not occur in a single tank but passes through multiple stages, each step removing more impurities and further concentrating the metal. As a result, from tons of initial ore slurry, only a thin layer of foam remains at the top, yet it contains a much higher concentration of metal. This is the concentrate that will be sent on for further processing. After being ground into fine particles, the ore moves into the separation stage, where platinum group metal particles are finally separated from the worthless rock using flotation. The mixture is fed into large agitated tanks and treated with specialized chemicals that make the metal-bearing particles hydrophobic. When air is injected, millions of tiny bubbles form. The metal-containing particles attach to these bubbles and rise to the surface, while the waste rock remains hydrophilic and sinks to the bottom. This process does not occur in a single tank but passes through multiple stages, each step removing more impurities and further concentrating the metal. As a result, from tons of initial ore slurry, only a thin layer of foam remains at the top, yet it contains a much higher concentration of metal. This is the concentrate that will be sent on for further processing. From here comes the most challenging step, removing all other metals from the mixture to obtain pure platinum, because even trace amounts of impurities can completely alter its properties. Using strong acid solutions, the mixture is dissolved and the reactions are carefully controlled so that each metal separates in sequence. In the end, platinum, the most inert and stable of them all, only begins to emerge once the solution has been almost completely purified. At this point, it precipitates out of the solution as a fine, pure powder, before being heated again to form gleaming platinum bars with a purity of up to 99.95%. This entire process, from dissolution and purification to precipitation, can take anywhere from 6 to 8 months or even longer depending on the mine and the technology used. Did you know that platinum prices have recently surged to their highest levels in nearly 4 decades, surpassing $2,000 per ounce? This upward momentum is expected to continue after Europe delayed its ban on gasoline-powered vehicles, extending platinum's role in catalytic converters for emissions control. From a metal once dismissed as a nuisance, platinum has become a symbol of luxury and status, rivaling gold. A multi-million selling record is certified platinum, ranking above gold, and even credit cards carry the platinum name, representing the highest tier in customer status and spending power. In fact, around 40 to 45% of all platinum mined globally each year is used to manufacture catalytic converters for automobiles. Inside these devices, platinum and other platinum group metals are coated as an ultra-thin layer onto a ceramic honeycomb core. As exhaust gases pass through, they accelerate chemical reactions that convert carbon monoxide and unburned hydrocarbons into less harmful compounds before they are released into the air. A critical function for meeting strict emissions standards around the world. But it is precisely because of those few grams of metal that catalytic converters have become targets of theft across the United States. According to statistics, catalytic converter thefts in the US have increased by more than 1,200% in just 3 years. For thieves, a single converter can fetch anywhere from a few dozen to a few $100s. But for vehicle owners, replacement costs often exceed $2,000, not including towing fees, repair costs, and the time the vehicle is forced to stay in the shop. As a result, many drivers have taken matters into their own hands by installing metal shields or reinforced steel cages around the catalytic converter. These armor-like protections not only make it significantly harder to access the part, but also force thieves to spend more time on the vehicle, often deterring them due to the loud noise produced during cutting or forced removal. Yet as electric vehicles continue to expand, a major question has emerged. If EVs no longer have exhaust systems, could platinum lose its role in transportation? The answer is more complicated than that. Battery electric vehicles do not need catalytic converters, but hydrogen fuel cells rely on platinum at the electrodes to split hydrogen molecules into protons and electrons, generating electricity in the process. In other words, platinum may leave the exhaust system only to become one of the most difficult to replace materials in clean energy technology. For the United States, this makes platinum a far bigger issue than simply the price of a precious metal, especially as most supply still depends on imports, particularly from South Africa. That means every mining strike, power crisis, industrial accident, or geopolitical disruption can directly affect supply chains tied to the automotive industry, hydrogen technology, and future clean energy strategies. It is the combination of rarity, durability, and extraction difficulty that has shaped platinum's exceptional value. In human perception, the scarcer and harder something is to obtain, the more valuable it becomes. And platinum is a near-perfect example of that principle. It is no longer just a metal, but a symbol of purity, resilience, and ultimate prestige. If gold represents wealth, platinum represents a deeper tier of value, where scarcity, resistance to time, and irreplaceable function are what truly define worth. The journey of aluminum's rebirth begins in places that are often overlooked: trash bins, scrap yards, and collection points across cities. Used beverage cans, discarded metal fragments from daily life and industrial production are gathered from multiple sources, ranging from households to industrial facilities. Thanks to its high recovery value, aluminum is rarely left behind. Instead, it is almost always reclaimed through recycling systems, scrap collection networks, or specialized recovery programs. After collection, the aluminum does not immediately enter processing plants. Instead, it is transported to intermediate consolidation facilities. Here, it is accumulated and compressed into large bales for easier storage and industrial-scale transportation. This marks a crucial transition, moving from scattered individual items spread across different locations aluminum is gradually consolidated into a large, unified stream of raw material, ready for the next stages of intensive processing inside recycling facilities. After being collected and transported to the recycling facility, aluminum enters the sorting stage, a critical process that determines the quality of the entire recycling chain. At this point, large bales of scrap aluminum are placed onto conveyor belts and passed through a series of automated separation systems. Magnets are used to remove ferrous metals, while eddy current technology helps separate aluminum from plastics, glass, and other non-conductive materials. Beyond that, aluminum is further sorted in detail according to alloy types and intended applications, such as beverage cans, industrial aluminum, or construction materials. Even slight differences in metal composition can affect the quality of the final product, making precision at this stage extremely important. Once sorting is complete, the aluminum is effectively material cleaned and ready for the next stages of processing. After sorting, the aluminum is fed into high-capacity crushing systems, where cans and metal fragments are cut and broken down into thousands of smaller pieces. Under the force of intense cutting and impact, the original rigid structure is completely broken apart, turning the aluminum into uniform shreds that are easier to process. This step does more than simply reduce size. It plays a crucial role in optimizing the subsequent stages. Once the aluminum is shredded, its surface area increases significantly, allowing processing to occur faster, more efficiently, and with lower energy consumption. At the same time, the improved uniformity and particle size helps ensure better control over metal quality throughout the recycling process. After being shredded, the aluminum moves on to a deep cleaning stage to remove any remaining impurities. Although it has already been sorted, the metal surface may still carry layers of paint, ink, grease, and organic compounds left from its previous use. The aluminum pieces are passed through thermal and mechanical treatment systems, where high temperatures help break down and burn off paint, printing ink, and organic residues. At the same time, additional separation and filtration systems remove any remaining ash and fine particles, leaving the metal surface cleaner and more uniform. This is a particularly critical step, as even a small amount of residual contamination can directly affect the quality of aluminum after melting. After impurities have been removed, the aluminum is transferred into industrial furnaces, where temperatures are raised to around 660 degrees Celsius, high enough to completely melt the metal. Under extreme heat, solid aluminum pieces begin to soften, deform, and gradually lose their original structure, merging into a glowing stream of liquid metal. During this process, aluminum is not simply melted, it also undergoes a form of refining. Lighter impurities such as residual paint, dust, and unwanted compounds rise to the surface as slag and are removed. At the same time, the high temperature fully breaks down old bonds, allowing the aluminum to return to a more uniform and purified state. Modern furnaces are designed to precisely control temperature and internal conditions, ensuring even melting, minimizing material loss, and preserving optimal quality. Once formed, the molten aluminum is kept in a stable state, ready for the next stages of production in the processing line. After reaching a molten and purified state, the liquid aluminum is transferred directly from the furnace into casting systems. Here, the glowing stream of metal is poured into large molds, where it begins the transition from liquid to solid. Depending on its intended use, aluminum can be cast into large ingots, thick slabs, or long billets, serving as intermediate raw materials for subsequent processing stages. This casting process requires strict control of both temperature and cooling rate. If cooling occurs too quickly or unevenly, the metal's internal structure may be compromised, leading to reduced quality. Conversely, when properly controlled, aluminum solidifies into a stable structure with the required strength and durability. As the molten metal gradually cools and hardens within the mold, aluminum once again takes shape, but this time, not as scattered fragments as before, but as uniform solid blocks of metal ready for the next stage of processing. After the aluminum has been poured into molds and begins to solidify, the metal blocks cannot be removed immediately. At this stage, they are cooled with water, typically through continuous external water spraying systems that rapidly reduce the temperature and stabilize the internal metal structure. The strong flow of water strikes the red-hot surface, producing thick clouds of steam, a clear sign that the cooling process is actively underway. Once the temperature drops to a safe level and the aluminum has fully solidified, industrial cranes come into operation. Massive cylindrical aluminum blocks, weighing several tons, are securely gripped by specialized mechanical clamps and carefully lifted out of the molds with high precision before being placed onto the factory floor. This entire process requires close coordination between machinery and technicians to ensure the blocks are not deformed or damaged during handling. At this point, the surface of the ingot still retains characteristic wave-like textures formed during solidification, while internal heat has not yet fully dissipated, meaning they must continue to be carefully monitored and controlled before moving on to the next stage. After cooling, aluminum slabs are fed into the rolling line, one of the most critical stages that directly determines the quality of the final cans. Here, the aluminum passes through a series of high-strength steel rollers where it is subjected to extreme pressure to gradually reduce its thickness. From blocks tens of centimeters thick, the aluminum is rolled through multiple stages, with each pass only slightly reducing thickness to avoid damaging the metal's internal structure. This process typically combines both hot rolling and cold rolling. In the initial stage, aluminum is rolled while still at high temperature, making it easier to deform and requiring less force. It then continues through cold rolling at lower temperatures, which increases strength, hardness, and improves surface finish. Between rolling cycles, annealing treatments are applied to restore the metal's ductility after it has hardened due to deformation. The result of the entire process is extremely thin aluminum sheets, typically around 0.2 to 0.3 millimeters thick for beverage cans, while still maintaining high strength, pressure resistance, and uniformity. These sheets are then wound into large coils, weighing up to tens of tons, and transported directly to production lines, where they will be stamped and shaped into finished cans. From these thin aluminum coils, the material enters high-speed stamping lines, where it is cut into circular discs and then deep drawn into the initial cup shape. From there, these aluminum cups are further stretched and thinned into can bodies through a drawing and ironing process, reducing wall thickness while maintaining the necessary strength. The rim of the can is precisely trimmed and formed to fit the lid, while the body is cleaned, printed, and coated with an internal protective layer to ensure food safety. Finally, the completed cans undergo a series of rigorous quality control checks, including tests for airtightness, structural integrity, and dimensional accuracy. They are then stacked and packaged in large batches, ready to be transported to filling plants. There, the cans are cleaned one final time, filled with beverages, sealed and labeled before being released to the market, appearing on store shelves as fully finished products, ready to reach consumers. Unlike most other materials, aluminum never truly reaches the end of its life cycle. It it simply keeps transforming from one form to another, again and again. With each recycling cycle, aluminum not only retains its original quality, but also saves a tremendous amount of energy compared to producing it from raw materials. This is what makes aluminum one of the most sustainable materials ever created, where the concept of waste almost doesn't exist, but instead marks the beginning of yet another life cycle. Living in a consumer civilization that has turned millions of square kilometers of ocean into massive, dead zones, the disappointment of a teenager during a diving trip sparked the largest ocean cleanup campaign in human history, removing more than 110 million pounds of plastic from river systems and oceans across the planet. After being collected, millions of pounds of plastic are transported into massive processing lines, where they are sorted, cleaned, shredded, and regenerated into raw materials for an entirely new industry. So how can these gigantic floating garbage zones be intercepted, collected, and processed on an industrial scale? Join Agriculture Insight as we explore the story behind this extraordinary achievement. Amid the massive ocean currents of the North Pacific exists a region containing trillions of pieces of plastic swirling endlessly for decades, covering an area of approximately 1.6 million kilometer squares, or roughly 3 times the size of France. And the world does not have just one, but as many as 5 gigantic ocean garbage patches like this. These are not solid floating islands of trash as many people imagine, but rather a plastic soup dispersed across an enormous area where ocean currents continuously gather plastic from all over the world. But the real danger does not lie in the massive pieces of plastic visible to the naked eye. It lies in the process by which they are continuously broken down by sunlight, ocean waves, and friction over many years until they become nearly invisible microplastics. These particles then enter the marine food chain and eventually return to the human body itself. In ecological logic, every year of delay in cleanup means all future intervention efforts become more complicated and expensive. But humanity delayed that process for more than 7 decades, ever since petroleum-based plastics began exploding on a global scale in the mid-20th century. Scientists estimate that this region accounts for only about 1% of the world's ocean water, yet contains up to 7% of all floating surface microplastics globally, equivalent to around 1.8 trillion pieces of plastic with a total mass reaching 100,000 tons. For many decades, experts almost unanimously agreed that cleaning this area was impossible. Estimated costs reached tens of billions of dollars. And using traditional methods such as ships and nets, the process could take thousands of years. But right in the middle of what seemed like a hopeless situation, a bold idea began to emerge. Instead of chasing plastic across millions of square kilometers of ocean, humanity would let the ocean currents themselves concentrate the waste in order to capture and transport it into massive industrial processing systems before it permanently degrades into microplastics. It was an approach that went against conventional intuition, yet perfectly aligned with the way the ocean itself operates. And to turn that seemingly irrational idea into reality, a 16-year-old Dutch boy named Boyan Slat emerged with an approach completely different from every ocean cleaning method that had existed before. 1 year after a disappointing diving trip off the coast of Greece, where he saw more floating plastic bags than fish, in the fall of 2012, at the age of 18, Boyan Slat stepped onto the TEDx Delft stage with an 11-minute talk titled, how the oceans can clean themselves.
However, I believe the Great Pacific Garbage Patch can completely clean itself.
For months, Slat's seemingly naive question received almost no attention and gathered only around 2,000 views. But by February 2013, when technology and environmental media outlets began discovering it, everything changed almost overnight. Donations quickly started pouring in, forcing Slat to make the biggest decision of his life: continue pursuing his aerospace engineering degree or drop out of university to chase the ambition of cleaning the oceans. At the time, his bank account contained only around $300 in savings. Slat chose the ocean. Just days after the video went viral, the project received approximately $90,000 in donations. And by September 15, 2014, the total had reached $254,282, becoming the most successful non-profit crowdfunding campaign in history at that time. And from that moment on, in order to prove that the oceans could truly clean themselves, the Ocean Cleanup was officially born, with its first mission keeping millions of pounds of plastic stationary in the middle of the ocean. The Ocean Cleanup first had to solve an extremely complex physics problem: how to create a structure light enough to continuously float on the ocean surface, yet durable enough to withstand large waves, ultraviolet radiation, salt water, and mechanical stress for years in the open sea. The system's greatest distinction lay in its gigantic mechanical structure, designed as a U-shaped floating barrier approximately 600 meters long. To create this structure, the Ocean Cleanup used around 50 sections of high-density polyethylene pipe, each nearly 1.2 meters in diameter, a material commonly used in offshore oil and gas systems because of its corrosion resistance, impact durability, and ability to maintain stable buoyancy in harsh marine environments. Most importantly, the assembly joints were built using steel connectors, reinforced cables, and flexible linkages that allowed the entire structure to bend with the motion of the waves rather than resist them. Beneath the floating pipes, engineers installed a 3-meter-deep skirt made of technical fabric. This depth was carefully calculated to retain most plastic floating near the surface, while still allowing marine life to swim underneath, reducing the risk of harming the ecosystem. The operating principle of System 001 was based on a very small difference in movement speed between the system and the plastic waste. While floating plastic is pushed faster by wind and waves, Wilson generates greater hydrodynamic drag, causing it to move slightly slower and gradually funnel debris into the curved central section like a gigantic floating trap in the middle of the ocean. In September 2018, System 001, nicknamed Wilson, was officially towed out of San Francisco Bay to begin its first real-world test in the largest garbage patch on Earth. However, the system quickly revealed serious limitations. Unstable ocean currents and inconsistent drifting speeds prevented the system from keeping plastic concentrated inside the barrier, causing much of the debris to escape back into the ocean instead of remaining trapped for collection. By the end of 2018, an 18-meter section fractured due to material fatigue at welded connection points, forcing the system to be towed back to Hawaii after collecting only around 4,000 pounds of plastic in 4 months. The figure was far below initial expectations.
We've developed a system.
As a result, System 001B was introduced in 2019, an upgraded version designed specifically to solve the problems that had caused Wilson to fail. Beneath the system, a parachute-style floating anchor approximately 6 meters long creates additional hydrodynamic drag, allowing the entire structure to move about 0.3 to 0.5 meters per second, slower than the floating plastic on the surface. This very small speed difference is enough for tens of thousands of plastic fragments to continuously accumulate in the central area, while retaining thousands of pounds of waste during each collection cycle. After around 6 to 8 weeks of operation at sea, the plastic accumulated in the center of the system is lifted onto the support vessel using industrial cranes. On the ship's deck, workers begin preliminary sorting of fishing nets, hard plastics, large containers, and organic contaminants before all the plastic is packed into containers and transported to recycling facilities. This process is extremely difficult because much of the plastic has drifted through the ocean for years, exposed to saltwater, UV radiation, and marine organisms that degrade and contaminate the material, making sorting and recycling far more complex than conventional land-based plastic waste. Its composition is also astonishing. Fishing nets account for 46% of the total mass, while between 75% and 86% of the plastic originates from offshore fishing activities. After more than 10 upgraded versions since System 001 Wilson, by 2025, the ocean cleanup had removed more than 25,000 tons of plastic waste from river systems and oceans worldwide, equivalent to the mass of tens of thousands of gigantic Labubu figures being pulled back out of the sea. But the ocean cleanup quickly realized that cleaning the oceans alone was not enough, because around 1,000 rivers, representing less than 1% of the world's river systems, are responsible for nearly 80% of the plastic continuously flowing into the oceans every year. Among them, Thailand, China, Indonesia, the Philippines, and Vietnam alone release as much ocean plastic as the rest of the world combined. This discovery changed the nature of the problem itself. Instead of focusing solely on cleaning up plastic that had already drifted into the ocean and dispersed across millions of square kilometers, the organization shifted toward a strategy of intercepting plastic at highly concentrated entry points, where river flow and geometry allow for far more efficient intervention in terms of energy and cost. From this logic, the Interceptor system was developed as an automated river plastic collection platform. Each system is approximately 24 meters long, nearly 16 meters wide, and permanently anchored along riverbanks using heavy-duty piles and tension cable systems. Extending from the Interceptor's main body, a floating barrier stretching dozens of meters is positioned diagonally along the direction of the current to continuously guide floating waste toward the central intake opening. As debris approaches the system, an automated conveyor belt approximately 1.5 meters wide begins operating, continuously lifting plastic from the water surface into the vessel. The entire system operates on solar energy, using around 32 solar panels installed on the roof to power the conveyor belts, sensors, and AI systems that monitor waste flow in real time. One of the most notable projects in the United States is Interceptor 007, deployed on the Los Angeles River, one of the most plastic-polluted urban rivers in America, where more than 220,000 pounds of waste were intercepted within the first months of operation before reaching the Pacific Ocean. But pulling millions of pounds of plastic back out of rivers and oceans was only the beginning. The next challenge was how to transform that chaotic mass of waste into reusable industrial raw materials on a massive scale. As soon as the material is brought back to land, the entire volume begins undergoing a careful sorting process based on polymer type, aging level, and recyclability. In reality, around 80% of the collected plastic has deteriorated and become contaminated to the point where it is no longer suitable for commercial recycling. This portion is typically processed through energy recovery systems or strictly controlled destruction methods to permanently remove it from the environment, instead of allowing it to continue breaking down into microplastics in the ocean. Only around 20% of the plastic remains stable enough to proceed into material regeneration lines. This mainly includes hard plastics, HDPE, polypropylene, and especially nylon fishing nets with lower levels of degradation. After being separated, the plastic continues through large high-pressure washing tanks to remove salt, sand, oil, and attached marine organisms before being fed into high-speed industrial shredders. Here, the material is cut into fragments several centimeters in size before continuing through polymer separation systems using optical sensors and float sink density sorting. The plastic that meets final quality standards is then melted at temperatures of approximately 180 to 280 degrees Celsius inside industrial extruders before being stretched into strands and cut into small recycled plastic pellets. Because of the extremely high costs of collection, transportation, and processing, ocean recycled plastic is often sold at prices up to 5 times higher than conventional recycled plastic, ranging from around $2,000 to more than $5,000 per ton, depending on material quality and purity. These plastic pellets are then sold back to manufacturers to produce sunglasses, packaging, electronic components, furniture, and many commercial products labeled as ocean recycled plastic. Some recycled ocean plastic has now even begun appearing in globally distributed commercial products. Coldplay once partnered to use plastic collected from rivers and oceans to produce recycled vinyl editions for one of their album releases, while Kia also partnered with the Ocean Cleanup to integrate recycled ocean plastic into next-generation automotive interior components. From a teenager standing in front of floating plastic bags in the Mediterranean, humanity has now, for the first time in history, begun truly addressing ocean pollution on a massive scale, proving that what was once considered impossible is sometimes simply a problem that has not yet been approached with the right way of thinking. By mid-2026, the Ocean Cleanup had removed more than 110 million pounds of plastic waste from rivers and oceans, operating 21 interceptor systems across 10 countries, with a team of around 200 employees from all over the world. The estimated cost of completely cleaning the Great Pacific Garbage Patch is $7.5 billion over 10 years, and the mission remains unchanged, removing 90% of floating ocean plastic by 2040. Even so, the amount of ocean plastic currently collected and recycled still accounts for less than 1% of the global plastic recycling industry, while the world continues producing more than 400 million tons of new plastic every year. And as plastic continues flowing into the oceans every single day, this battle has perhaps only just begun. In your opinion, what is more dangerous? The millions of tons of plastic already floating in the oceans, or humanity continuing to produce more of it every day? Plastic is not the only material that modern civilization is learning how to regenerate, because every year hundreds of billions of glass bottles are also entering one of the most complex industrial recycling systems in the world.
The plastic graveyard stretches for miles.